Hello, my name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and together with the ACMA, the American Composites Manufacturers Association, we are hosting today's webinar on graphene and composites, better, lighter, and stronger. Before we get started, I'd like to just share with you a little bit of information about the Graphene Council. We were founded in 2013, and today we reach directly 30,000 material scientists, both in academia and in the commercial section, that are working with graphene, and we're also actively involved in developing standards for this material. A short list of the members that we have from the Graphene Council shows that we have the entire ecosystem, from raw material suppliers to academic and university-based researchers, through graphene producers and important end users. And it's our mission to connect this global community. One of the reasons graphene is such an exciting material is that it has so many potential applications, and we've identified more than 45 different ways that graphene can be used to dramatically improve the performance of other materials or applications. The Graphene Council is not only a trade and professional body, but we can also provide custom consulting and advisory services. And we are also the authors of the Graphene Report, a more than 600-page document that outlines production methods and processes, characterization techniques, forms of commercially available graphene materials, market pricing data, standardization information, different applications and commercial markets. And we also profile more than 200 graphene producers worldwide. The Graphene Council is the largest body for this sector, and we are a Tier 2 member of the Graphene Engineering and Innovation Center at the University of Manchester. We are incorporated in the UK, in the United States, in Switzerland, and have an office in Brazil with the McGrath Institute at Mackenzie University in Sao Paulo. This is just one of a series of webinars that we are providing to help educate end users in particular about how to unleash the potential for graphene materials. We've also developed white papers on graphene use in aerospace and automotive applications as platforms. And we also have a collaborative project testing 15 different forms of graphene material head-to-head in a standard resin system to really evaluate how graphene can improve important mechanical properties and see which form of graphene, because there are many different types or morphologies of this nanomaterial in a resin system. And so they have independent third-party testing data that will be made available to the public. And that testing program is done in conjunction with the University of Manchester. At this point, I'd like to introduce Dan Coughlin, who's representing the American Composites Manufacturers Association, to give us some introductory remarks. And I'm very, very pleased to be working together with Dan.
Thank you so much for inviting ACMA to participate in today's webinar. Welcome to all those who are in the meeting. Well, thank you so much. And, I'll just give some brief introductory remarks. Really interesting to see the content from the University of Manchester, where graphene got its start. But just a little bit about the American Composites Manufacturers Association. I'm Vice President of Composites Market Development. And just one thing, we do conduct all of our meetings in compliance with ACMA's antitrust policy. Please let me know if you have any questions regarding compliance with that policy. But ACMA is an association of companies. We have over 500 member companies, and there are many people within those companies who are members. But we have the mission of supplying education, outreach, advocacy, and basically everything needed to help grow the share of the composites market in the US and around the world. And graphene is definitely an interesting opportunity to do that, as evidenced by the large attendance at today's meeting from all over the world. Just kind of briefly, what are we hearing about composites lately? Some markets are seeing loss of business, while others are holding steady or growing. But there are growth opportunities. It's not business as usual. We are connecting a lot of our members with new opportunities for growth. Collaborating up and down the supply chain, and graphene is probably a great example of this, is really important because it's an additive, but a very important additive. And a lot of materials come together to make composites by definition. They're heterogeneous materials that have unique properties. But in terms of the business plans being reworked for the current and near future climate, we're helping our members with those, with an emphasis on sustainability, not just recycling and life cycle analysis, but sustainability of businesses as well. But we do see, because of the disruption, an acceleration of a lot of trends going into the COVID crisis are accelerating coming out of the crisis, meaning people are looking to new applications, and there are many white space opportunities out there for composites to gain market share. And certainly graphene, like I said, is one of those opportunities. I won't belabor this slide. It just kind of goes into the different markets the composites reaches, and I think graphene has applicability in all these markets, including architectural, infrastructure, construction, sporting goods, wind energy, of course, would not be possible without composites, automotive, and of course, aerospace, defense, and marine. I think I've already covered this, so I'm going to move on to some market development activities related to our Technology Day programs and OEM roundtables, where we connect our members to kind of the latest and greatest needs within the end user community regarding composites. And we have divisions in all the various market segments. As I said before, we represent everything from aerospace, architectural, through infrastructure, construction, even advanced air mobility, automotive, and high performance, which takes in aerospace, defense, wind, and compressed gases. Just to give you, and again, everyone will get a set of these slides, our High Performance Council probably is where folks would land first if they came to ACMA. If you're not already a member, you see some of the companies who are members off to the right. We have OEM hosted events where they help our members understand what the opportunities are in composites. You see a list of the companies there that have been hosted by the High Performance Council, and there's an equivalent list in the automotive area that I won't go over today, but it can definitely help if you're interested in that. So our Technology Day programs, I'll just touch on this quickly, are private member-only events where we speak with one voice as an industry and help educate and bring the message of composites to the end users that are out there, that many of whom did not get training in composites in their primary education. So we see education as one of our primary duties at ACMA. And just sort of leaving you with some events you won't want to miss. You just missed our Spirit Aerosystems Tech Day, where we had 190 thought leaders from Spirit Aerosystems from around the world. Our VW Group Tech Days, I think there are still a few slots left. We'll be going from January to April in weekly meetings with folks from around Volkswagen Group. Infrastructure Construction Tech Day this winter. And we'll be having a fly-in related to various categories, including automotive defense. If you want to know what's happening in regulatory and what's happening on Capitol Hill, please attend that series the week of March 9th. Then we have our Pultrusion Conference in April. The Composites Industrial Revolution Conference coming up in May is really about Factory of the Future, or Industry 4.0, specific to composites. And we've pretty much filled up that event, so that we're looking forward to that event, which is a 3-day event in May. And then supply chain, what's happening with supply chain locally and globally in composites. That will happen June 15th and 16th. And then, of course, CAMX will be all those are virtual, but CAMX will be in person this year in October in Dallas, and hope to see you there. Happy to answer any questions. Please contact me if you have any questions. I know I went through that rather quickly, but I really wanted to leave time for our featured speakers today from the University of Manchester, Mark and Arun.
Okay, so first of all, Terence, thank you very much for inviting us to speak today. We appreciate it. So we will cover the key markets for carbon fiber reinforced plastics and wire graphene, commercial successes and developmental work in graphene and CFRPs, and also Aaron will then carry on with challenges in graphene adaptation and opportunities for graphene carbon fiber reinforced plastics. What you're seeing for us now was all pre-COVID. So these numbers, I don't know if they'll still stand or not, but pre-COVID, the global composite market stood at around $106 billion for 2020. The global aerospace composites market stood at around $25 billion, estimated to be in 2025. And the UK aerospace market alone in 2020 was around £1 billion, and that was estimated to be rising to £3.5 billion by the year 2030. As you can see from the Boeing 787 Dreamliner demonstration below, you can see where the growth in the composites market is coming from. Predominantly is the aerospace market and how aircraft are designed and built today. You can see that nowadays 50% of an aircraft is used by composites. So you can see carbon fiber laminates or carbon fiber sandwich panels or other composites for internal like overhead luggage compartments and things like that are all made out of composites nowadays. The global demand for composites, just carbon fiber alone, is estimated to be around 117 kilotons by 2022, and the carbon fiber reinforced plastic market is estimated to be around 194 kilotons by 2022. Just also, you can see below there the fleet developments, which you can see is pushing up the demand for carbon fiber reinforced plastics. So he's thinking in 1992 there were only just under 12,000 aircraft in the sky. Now you can nearly quadruple that for 2032, which is estimated to be around 41,000 aircraft in the sky. So that is really pushing demand up for carbon fiber composites. So why carbon fiber composites? It lends itself to easy design. I mean, it makes life easy for the design of aircraft parts, high specific strength, high specific stiffness, low density, chemical resistance, low coefficient of expansion, ease of integration, part consolidation, and freedom of design. All lends itself to aerospace, automotive, marine industries, making parts easy design, makes them more flexible, makes them lighter. I mean, today in this age, the push for reduce the amount of fuel that is used in aircraft and other industries is massive these days. So lightweighting of aircraft, cars, marine, has all been pushed heavily just to reduce the amount of fuel that has been used. Adding graphene to that, and what makes graphene special? I mean, graphene, if you think, is 1/1,000,000th of the thickness of a human hair. But from that, as a single layer, it is the highest thermally conductive material known to man, the highest electroconductive material known. It's chemically modifiable, so we can make it fit, adapt it to whatever we want to make it fit to, whether it's chemical resistance or putting it into carbon fiber prepreg, so it enhances the resin systems easy. You can add it to the resin systems a lot easier and just without the functionalization. High tensile strength, so as a single layer, it's 200 times stronger than steel as well. High surface area, it's flexible, so we can make flexible components such as flexible batteries and things like that in screens. So it doesn't just lend itself as one thing to a new component, it is multifunctional. So it brings that multifunctionality to a new component. So existing and developmental commercial graphene carbon fiber reinforced plastic applications, some that we know of so far. So the BAC car is a single-seat road car, which is designed and built in Liverpool in the UK. Now these guys have developed a graphene-enhanced carbon fiber car, which is actually in the market. I know that for a fact that they have sold all those cars to date. But they didn't just design new parts for the car. They actually started by designing new tooling for the car to make the actual components. So they use graphene-enhanced prepregs to make the tooling. So what that did was improve the thermal conductivity of that tooling, so they could process it quicker, so it would heat up in the autoclave quicker, it would cool down quicker, so they could take the parts out sooner, which decreased the actual process time required for manufacturing the car. So from that, they also designed new components. They designed a component prepreg, which used less than 1% graphene in its resin system. But from that, the improvements for stiffness and tensile strength, they managed to increase that by approximately 50%, which in turn allowed them to use less materials in their parts, which overall saved them around 20% in the total car weight. And if you think that the car itself only weighed 600 kilos to start with, that's quite a saving. And also enables their customers to drive around a track a lot quicker than what they would do normally. So aerospace applications, one of the aerospace applications which we've seen, which I'm sure most people have seen, is the Airbus A350 leading edge. So this was part of the Wing of the Future project with Graphene Flagship. I mean, this was using a Hexflow RTM6 resin system, which they had a graphene to, and put it through an RTM process. So they managed to increase the mechanical properties and also decrease the fracture speed of the component when it was in use. So by increasing the mechanical properties, they were able to also use less material, which gave it a thinner edge. The actual component itself was a lot thinner, a lot lighter, and a better product altogether. So this is a UAV called Juno, which was developed by the University of Central Lancaster, along with Haydale and ourselves at Manchester University. As you can see from that, it's the prepreg is used in the fuselage and the wings as well. And also, if you look at the end of each of the wings, you'll see a blue sticker and a purple sticker, and those are actually 3D printed from the plastic parts, with the winglets, which are then bonded onto the carbon fiber wings themselves. So it's covered multiple areas of where we can add graphene to different composites. And the next generation for the Juno will have a graphene enhanced battery. We yet to decide what it's going to power as yet, but it will be added to the next generation. So this is looking at thermal conductivity. Actually, this is an interesting one. This is for those in manufacturing of carbon fiber components. This, you can see, is a mandrel tool for a wing spar for an aircraft. It's 10 meters long. The customer had problems with microcracking in their tooling system, and tools were having to be replaced quite often. So it became very expensive for them to use carbon fiber tooling. So what these guys did at Applied Graphene and Composite Tooling Engineering Solutions, Retract SHD, they developed a graphene enhanced prepreg, which was used just as a surface ply and used in areas where it was required. And what the matrix did, the graphene toughened the matrix, and that reduced the actual microcracking over the repeated cycles, so it extended the tool's life cycle. And in fact, I think that tool is still in service and hasn't had to be replaced as yet. So the costs have been driven down, and the customers using those tools now are very happy. So this is a lightning strike. Again, this is with a company called Haydale. So this was looking at trying to replace the copper wiring in the wings for lightning strike and aircraft. So you might say increase electrical conductivity, a carbon fiber reinforced plastic with a graphene enhanced epoxy. You can see there on the left without the scorch marks, without the graphene, and the one with the graphene, the actual scorch marks. There's no scorch marks whatsoever from the testing, so it didn't really touch it. But also on the back of that, like I mentioned earlier, about multifunctionality, they actually managed to increase the modulus in the material as well. So increase that by 16 to 20%. And this material has actually been in an aircraft, a demonstrator, in 2017. So that was a very successful demonstration. And this material is now actually available in the market. You can actually buy this. It's commercially available. So another area where graphene prepregs have been used is sporting goods. The gentleman, the athlete you see here, his name is Don Parsons. He's a British Winter Olympian. And he won the bronze medal in the skeleton bob in 2018 on a graphene enhanced skeleton sled. So what they found was that the improved toughness helped with the dampening of the vibrations from the actual run through the runners into the athlete as well. So not only in toughness, but the dampening enabled Dom to be more comfortable on the sled. It stopped vibrations, so he could then control it better, and it was a lot better. So he could manage to control the sled a lot better. So this, at the time we got this, was said to be the lightest kayak of its class in the world. I don't know how true that is anymore. I'd say it's back in 2018. But what these guys did, they added graphene to a resin system, and then called Hexabond, and then made a prepreg material with that. And what they found was the 24% increase in strength, which then enabled them to reduce the amount of material which was used. So they managed to save a total of 10% reduction in weight. And again, over something that size, 10% reduction in weight is not is quite significant. So it's a really good test of graphene there. This is one of my favourite projects. One was done with Applied Graphene Materials. This is a cryogenic pressure vessel. So this is what we call like innovation on innovation. I don't know if people know or were aware about pressure vessels, but normal pressure vessel is cylindrical, like a fire hose, a fire extinguisher. So what these guys did, they part would contain graphene, and then they made a prepreg with that system. And what they found was with a non-graphene material, the vessel would fail after 10 minutes due to low temperature, causing microcracking. So the minus 184 degrees C and the pressure of 600 psi would cause microcracking in non-graphene material. When they added graphene to it, under ACMA, they noticed there was actually no microfractures at all, which enabled them to keep the pressure vessel safe. So it's a really good project, that one. It shows what graphene can actually do. So Orbex is a UK-based low-cost orbital launch service. So these guys put commercial satellites into space for their customers. They are looking at adding graphene to their carbon fiber body so they can reduce the weight. So hopefully when they reduce the weight of the actual rocket itself, they can then increase the amount of payload they can take up there into space, and or they can reduce the amount of fuel they require if they're keeping the weight the same. They can reduce the amount of fuel they're having to use to launch these rockets. A couple of other products and developments which are out there in the market. I'm not sure people are aware of these, but there's Dassi bikes, which was claimed to be the lightest bike on the market when it first came out. I'm not sure if you can still buy these bikes or not. I'm not sure. Fishing rods. Fishing rods are massive in the US. I know there's a company called G Rods in the US which have a number of fishing rods with graphene in their materials. Bumpers for automotive industry. This is a structural part for a bumper, and this was developed at the University of Sunderland under part of the graphene flagship again. So that part is now going to the next stage and hopefully getting into industry. And also we have graphene enhanced prepregs. There's a number of different prepregs now which are available on the market. I mean, it's not only our partners that are selling those, but there are several materials out there available for people to buy off the shelf and use in their products. That's a quick overview of what where we're at with graphene and carbon fiber. I'm going to hand you over to my colleague, Dr. Aaron Raju. So he's going to go through the challenges in graphene adaptation.
Thanks, Terence. Firstly, I'd like to thank Terence for giving us the opportunity to be presenting in this forum. It's a great forum. So I'll start off with the challenges in graphene adaptation. So the first one being, what are the common challenges that are existing in the fiber reinforced plastics? So fiber and the matrix themselves are two different materials with completely dissimilar physical and interfacial properties. Because of these two different properties, they have typically a weak interface, and because of the weak interface, any defects that can present in the interfacial area can lead to a sudden and catastrophic failures. And because of this property difference, and these two different materials have a completely two different thermal expansion coefficient, that could actually cause accelerated degradation as well. So it's fair to say that the FRP is a complex architecture in itself, and the production methods to produce these composites are quite complex because of the parameters that are actually being considered. So what are the commercial challenges that are there when it comes to graphene? So firstly, the raw material in itself. So there are several different types of graphene. And there's, compared to 10 years ago, there's a lot more graphene that you can actually count. There are several webinars that are happening within Graphene Council explains the different types of graphene as well. So you have to choose the right type of graphene for the right application, and that is the most crucial part when it comes to the designing any graphene for your application. So for example, graphene oxide is hydrophilic and it is water absorption. You could use it for water absorption, whereas graphene nanoplatelets are a type of, which is a hydrophobic, so you'd use it for electrical conductivity and all sorts. And when it comes to the actual raw material itself, the production, there is a lot of batch-to-batch variation when it comes to the raw materials, and the regulatory bodies are currently implementing standards to address that particular problem. It's fair to say that recently, in several years, the raw material manufacturers themselves are putting in quite stringent quality regulations within the production of their materials. So we're not actually seeing as much batch-to-batch variations compared to several years before. Of course, the second is the dispersion, how well the graphene is actually dispersed in the matrix form, and what are the best dispersion techniques that you have to use. Say, for example, do you have to use a high shear method or a low shear method, or do we have to implement any post-processing techniques that you have to do in order to have the dispersion in the final product. Say some may ask that the resin transfer molding procedure, filtration could be a problem. And there are techniques that currently that are implemented to avoid this filtration of graphene nanoparticles too. And when it comes to material design, one of the data that is lacking for end and prospective customers are the operation scenario or under several severe loading conditions and the data around it. But there are plenty of literature around or academic studies that can actually say the graphene is viable for certain applications. But when it comes to this operational scenarios under severe loadings, the data is quite limited on how open they are for end customers, and that's always the challenge. So moving on to modeling. So typically the graphene in the fiber reinforced the modeling around that is still in the early stages. The research and development are going in the right direction in order to advance in this particular field. The product development of graphene has always been specific for that particular application. So do development, but people who doesn't have any such sort of budget, it's hard for them to go without a knowledge of graphene and develop the products on their own. And still, there are some companies or some people who are still unaware of the presence of graphene or what it can actually apply, what can impart to their products. Complex resin formulation. As you all know, none of the resin as produced are used typically. They are either formulated with toughening materials or any other fillers to be as well. So there is an interfacial interaction between graphene and these other fillers. So that has to be considered when it comes to designing the material as well. So this is one of the challenges of adapting graphene in commercial application. So put cost in. Still, for some people, cost is also a factor. To be honest, back in 2011, I have bought 1 gram of graphene for 500 pounds. Whereas now you can buy a decent grade of graphene for a kilogram under $200. So typically the loadings of graphene you want to add into a fiber reinforced polymers are less than 1%, typically 0.5% in the resin. So you can go a long way. Health and safety, of course, health and safety of the materials, or how it can be handled, how it should be handled safely is another issue. So what are the opportunities of graphene carbon reinforced plastics? So just to in a general trend, how graphene are added into FRPs. So the first one is, of course, modifying the bulk matrix. That is by adding graphene into the resin system itself. That's one of the most easiest ways. And so one of the challenges is how do we actually keep it homogeneously dispersed. The second method is by adding the graphene epoxy onto the film in between the plies, for example. So either you could apply as a graphene as like a resin film, or the graphene can be spray coated in between the dry fabric or on the pre-preg themselves. So when in the cured laminate, the graphene actually lies in the interface between two different plies. Or then the third one is the graphene can be coated on top of the laminate directly, so it could act as for a barrier application. Or the other method is just to modify the surface of the carbon fiber themselves, either by grafting the graphene or graphene-based materials directly covalently to the carbon fibers, or you could possibly modify the actual sizing material by adding graphene or graphene oxide-based materials to it. So that can actually act as the interface between the carbon fiber and the matrix. And typically, the combinations of these are quite variedly studied. That is modifying the matrix and also modifying the surface of the carbon fibers seems to generally work for the FRPs. So this particular table I put in, so the data has been generated from over 500 articles from these two different references. I highly recommend, if anyone is interested in graphene carbon fiber reinforced plastics, to go and refer these articles. We have done a comprehensive review of almost all the carbon fiber academic studies and also the commercial studies as well. So as you can see, say for example, compression after impact is one of the crucial improvements that you properties for aerospace and also automotive industry. And improvements up to 25% seems to be a very a crucial improvement, or it can be appealing for a lot of industries as well. So I'm going to highlight a few properties that I feel very important when it comes to the carbon fiber plastics by addition of graphene. And one such is the fatigue improvements. So fatigue is nothing but a progressive damage of material under repeated cyclic loading. It is when a material is deformed under the elastic deformation levels. Because of the nature of its being deformed, there's a debonding that can happen between the matrix and the fiber or the reinforcement, which creates micro cracks, and these micro cracks can eventually become macro cracks, and the crack can actually propagate it, which eventually leads to the failure of the material. So anything that can be done to delay the progression of this crack, which increases the durability of the material. So that's what have been that's what graphene can actually help. So in this particular study, what they have done is by adding just with 0.3% of fuel layer graphene to the resin, they were able to increase the fatigue life of the material by nearly 15 times. When you compare it with the multi-work carbon nanotube, they were able to just do it for 5 times. So this can be easily explained in this study where graphene is used in just an epoxy itself. So this is a pretty neat study in which they've distributed the graphene in the resin by using different dispersion techniques. And what they've done is they've applied the electric current to see if they can align the graphene in the direction of the electric current. And as you can see, they have actually achieved it. And these samples have actually gone through a fatigue testing. So for example, in the neat resin, if you look at the crack propagation, and in front of the crack, there's nothing there in the front of crack to prevent it from going through, so it will eventually go to failure. Whereas when it comes to the randomly oriented graphene, for example, because of the fatigue deformation, as I mentioned before, there's a stress concentration that is there between the graphene and the matrix, which can create the debonding, creates the micro cracks, and because of the micro cracks, the crack actually propagates to these micro cracks, which means there is a crack deflection. And because of the crack deflection, it's absorbing more energy. Because of absorbing more energy, you're increasing the fatigue life of the material. And it's the same thing when it comes to the aligned graphene. The only difference is when the crack comes in contact with material or the graphene which is aligned vertical. So the crack has to even propagate even longer, or it has to go over through the over the graphene nanoplatelets, which means it's absorbing more energy, thereby increasing the fatigue life. So keeping on the fracture improvements, so this is you may have seen back in 2017, McLaren along with along with the University of Manchester collaboration, they've produced this beautiful piece of engineering. It's the first graphene watch, if you like. The whole watch just weighs 40 grams, including the strap and including all the components inside. And thanks to the frame, which is made with graphene enhanced carbon fiber plastics. So the graphene was actually added into the resin, which was then made into prepregs, and then was made into laminates, sheets, which was then machined to form the actual casing itself. So what graphene has done, you may ask. So what you can see here on the top is computer fracture tomography, X-ray tomography picture. You can see these are the graphene flakes, and these graphene flakes are typically large in dimension, probably 10 microns larger. And what they found is they seem to align in the direction of the UD fabric on the top, because maybe because of the filtration effect. What interestingly they found out was when they did the cross-section analysis, they were able to identify the graphene flakes, smaller graphene flakes, sub 2 micron or 5 microns, embedded in between the carbon fibers and reinforcing the matrix themselves. Because of the combination of these, they were able to see improvements in the axial property improvements, which is predominantly dominated by the carbon fiber themselves, which is quite interesting. So keeping the same theme, so as I mentioned, the larger graphene flakes align in between the laminates. So when a crack actually propagates, so what could happen is that because of the larger graphene flakes, the fuel layer graphene can separate, and this can actually lead to a weaker deformation. But when it comes to smaller flakes, what smaller flakes can happen, they can align in any sort of direction or in a 3-dimensional way. So when a crack actually propagates, it has to go through a lot of roots. So to actually crack propagate, so these small flakes can actually act like an obstacle for these cracks. So the take-home message for you from this particular thing is, it looks like the smaller dimension flakes works very well for carbon fiber reinforced plastics rather than the larger flakes, which are typically the case for rubber and plastic based material. So moving on to the multifunctional applications of graphene. So other applications, de-icing by Joule heating or the resistance-based heating. So in one of the studies, what they've done is they've produced graphene in polyvinyl alcohol-based material, which was then coated onto a paper, and they made the paper heater. And because of the resistance increase, there was heat increase, and application of current, and they can use the heat to as a heater itself directly. So this flexible heater was then converted into a carbon fiber laminate, which was then molded into this wing sort of structure. And they claimed that by heating it in a high density power, they were able to show this heater is very efficient, such that they heated up from minus 32 degrees to 0 degrees under 2 minutes. One of the important observations they found was it worked comparatively very well to the conventional silicon wires. They were able to perform it much better than the conventional silicon wire based heaters. And theoretically, they aim to melt that 1 millimeter thick ice from minus 32 under 9 minutes. And this particular study was done on a glass fiber reinforced plastic, but still is very relevant. Because you can see the methodology behind it. So individual glass fiber rovings were actually coated with graphene or based inks, which was, again, it was very highly conductive on the surface. And they used the surface conductivity to actually heat up work as a heater, basically. And they've seen this heater performs from minus 0.1 degrees to 27 degrees C under less than 5 minutes. So you can see the multifunctional gains that you can obtain apart from just adding graphene for the reinforcement. You can actually apply other reinforcement, other application development as well. So fire retardancy is another area where graphene has seen a lot of improvements. So apart from what they found is by adding graphene along with other existing fire retardants, we've seen very good improvements in the fire retardancy. For example, DOPO is a non-halogenated fire retardant which is being used. By adding graphene to the DOPO, they were able to even improve the entire composites UL94 properties. And in another study, they managed to graft chemically the DOPO onto the graphene oxide, which was then used to produce the CFRPs. And just with the 3% loading, they were able to increase the limited oxygen index from 18 to 28%. And you don't necessarily have to add the entire graphene to the whole system. In another study, what they've done is they just added, of course, a lot of graphene, but still they've only added the graphene on the surface layer, surface ply, and still they were able to decrease the heat release rate by 35%. The way it works when it comes to the fire retardancy, it seems like the graphene, when the fire, it actually forms like a protective char layer, and this char layer prevents the heat to actually penetrate through the material, which means it is increasing the tortuosity for the heat to go through. And besides that, what graphene can do is it actually restores the mechanical properties that are typically lost because of the flame retardants that are being used. So another area is graphene to be used in the actual sizing itself. Graphene has actually enormous potential in the sizing industry, and typical sort of improvements that you can actually get is up to 40% on the interlaminar shear rate. It's quite compelling for a lot of industries. Advantage is that it could actually disrupt the market. But in the recent developments being the sizing formulations are typically water-based. So graphene oxide-based sizing material seems to be widely studied, and it's very stable as well. And one notes that we got from the sizing industry is that the actual sizing itself for actual commercial application doesn't need to be staying for quite a long period of time. A 72-hour stability is more than enough, because that is the time until it takes for the sizing to be produced and to be applied onto, for example, like glass fiber itself. So if the actual graphene-based formulation on a sizing, if it is stable for 3 days, could be enough. The challenges is the sizing market, as you know, is one of the highly trade secret. So you'd have to find a sizing formulator, or you have to work with the carbon fiber manufacturers themselves to work on this particular industry. Another interesting application area which has seen a lot of press recently, and it's a very interesting piece of science that was developed earlier this year. By adding graphene to the carbon fiber precursor, that is polyacrylonitrile, you can actually improve the properties of the actual carbon fiber itself. So this study have shown by adding just 0.0758% of graphene have increased the strength and the modulus by quite a way. And the way it actually does this is because during the actual drawing procedure, the graphene actually aligns in the direction of the drawing. It actually helps in altering the microstructures, and which means the whole carbon fiber is compact, and it's actually producing a very good mechanical properties. Of course, the challenges being how it can be actually adapted into the actual industry itself, and how well batch-to-batch variations. And of course, this is an initial study, but it still shows that quite a lot of applications that actually can develop. So other property improvements I quickly touch upon is as I mentioned about the moisture barrier. So one type of material, that is graphene oxide or reduced graphene oxide, can be used as it has a hydrophobic properties which you could tap into to produce a hydrophobic material. So in one of the studies, they were showing improvement from 82 to 127 degrees improvement in the contact angle, and they were using this particular material as a corrosion protection for a cold rolled steel application. Thermoplastic carbon fibers. There was a webinar yesterday about graphene in the thermoplastics industry. So I put the slides in just a study in to show graphene can actually help in already high performing material, which is PEEK carbon fiber. So what they have done is they have surface modified using a plasma to increase the adhesion of this graphene. And they were able to hot press these laminates together, and this laminates, it's already high performing laminates, but showing an improvement of the short beam shear strength by 15%. So still there's a lot of development that can happen even within the already high performing materials. The recycled carbon fibers is another area. Interestingly enough, it's one of the areas which is least explored, and there is a lot of scope for development for either for the carbon fiber manufacturers, recycled carbon fiber manufacturers, or graphene product manufacturers themselves to find an application area, because recycled carbon fibers are currently being used in so many different applications, and it is even being used to make into fibers. So perhaps the graphene can actually enhance the adhesion, or you could probably up the recycled carbon fibers the performance as well. So in summary, of course, for the reinforcements, the graphene actually increases the fatigue and fracture toughness of the material, which further increases the durability of the material, which can be used as cross structures, for example. Lightweighting is huge. Anything to do with reducing the weight of the product, for example, in wind turbine or an automotive industry, it has a lot of weight to that. Conductivity, for example, both the thermal conductivity and the electrical conductivity plays an important role when it comes to graphene-based materials. Of course, you have seen commercial applications where graphene being used or tested as a lightning side protection. Often, of course, graphene-based heaters are being developed in order to use a de-icing application. And there is a big spearhead which is being developed within the graphene flagship, which is concentrating on this particular application. And multifunctionality obviously is another additional benefit that, apart from the mechanical and the lightweighting that you can get, you are looking to improve the flame retardancy and hydrophobicity of the entire composites. So I think with that, I would like to thank you everybody to be in this forum.
And so let me just kick off just quickly. There have been a couple of questions about recyclability. And Arun, you mentioned yesterday, of course, we did a webinar yesterday on graphene and thermoplastics. And so I would invite anybody who has an interest in this topic. The Graphene Council has a library now of webinars. We've done one on graphene nanoplatelets specifically, graphene oxide specifically, characterization methods specifically. thermoplastics yesterday, today on thermosets and composites. So if you need more information on that, we'll send out the links. But one of the questions I have for you is experience with recyclability, which is one of your last topics there. So folks are asking about how this affects recyclability. And we might tag on another question. Somebody asked, how does adding graphene to the pan manufacturing affect the performance of the fibers? And of course, there's a lot of recycled fiber use now. So I don't know if you want to tackle some of those questions.
So recyclability, I can talk in whatever I can share. So adding graphene to any recycled materials, for example, we have seen it actually improves the property of the recycled materials. Say, for example, recycled thermoplastics. So it actually improves the property of the recycled plastics up onto the virgin plastics themselves, despite it, no matter where it came actually from. So that is one of the important increases that we have actually seen. How recyclable the graphene-based materials is, do not actually look specifically into how many times the recycled graphene can be used back into the same thing. So that is a very interesting feature that I think everybody is interested in. So we are actually looking into those scenarios too.
Yeah.
When it comes to the second question of adding graphene to pan, so that, as I mentioned, is one of the recent studies that have come about earlier this year. So they have done only on the single fiber, allowing us the interfacial shear strength. So it would be definitely interesting to see how the study actually progresses to the fact that actually they can actually make a laminate out of that study. So.
Excellent. And Dan, I'm sure you have a couple of questions. Do you want to jump in here?
Oh, sure. Yeah, thanks. Great presentation, Mark and Arun. Just a question about the physics and engineering principles that account for the increase in material performance, whether it's conductivity or mechanical performance. Can you talk about the sort of graphene concentrations and formats that are used in those different applications? And I think you also, maybe you didn't really touch on thermal conductivity, but if you want to address that as well, I think that's of interest.
You want to go, Aaron? You want to start?
Yeah, so typically when it comes to the mechanical mechanical improvements, if you like, when it comes to fiber reinforced polymers, typically the loading weight percentages are predominantly less than 1%, or in fact even less than 0.5%. Added on to has shown a lot of improvements in the mechanical properties. Anything over 1% have in fact actually decreased the properties of the mechanical properties of carbon fiber or the glass fiber reinforced plastics. When it comes to obviously the thermal conductivity, you probably need a little bit more than 1%. You wouldn't be able to get the necessary thermal conductivity measurements or the electrical conductivity just with 1 weight percent. So you're looking like more like 5 to 10 weight percent. It is the way it can be engineered. So you need to be using where it is actually required. You don't necessarily be using to all the places. So it could be used like a conductive track, for example. So those are the real advantages of using graphene-based materials.
Yeah, great, thank you. And just a question about the material handling infrastructure, health and safety requirements of introducing graphene into a manufacturing facility. Can you just talk about that for a little bit, whether there are any special precautions that need to be taken to use graphene?
Yeah.
I suppose it depends on if they're using graphene powders or whether they're using it in a solution. If you're using powders, then yes, you have to have some sort of health and safety equipment, obviously face masks, fume hoods, things like that, so it doesn't go into the air. But most people who we're working with tend to get it in a solution, or we put it into a resin system for those guys already, so you don't tend to have to handle the graphene themselves. So it just depends on how people want to use it. But there's a lot of work going on around the health and safety in using graphene.
Yeah. Go ahead, sorry.
Yeah, specifically, so you could probably, one of the ways to, in an ideal scenario, an end customer would be using a graphene-based master batching, for example, which they can use it in a safe manner, which can ideally, use it. But currently, mean, you're just following the similar sort of protocols that are being used for example, carbon blacks or for carbon nanotubes. What is being followed is being followed for the graphene materials as well. Of course, it's still a high surface material, so you'd have to be using as Mark said, in a controlled atmosphere under the fume hood, add it in a slow manner. So those are all the know-hows that actually comes up by working with these materials.
And if you don't mind, I'll jump in just for a second. I mentioned before we're doing a composites head-to-head testing project. That material is being compounded, for example, by one of our partner companies, ChromaFlow, who's actually doing the dispersion. Part of the magic of getting graphene to work is in the dispersion process, which is an acquired skill. It depends a lot on the morphology of the particular material. And so we do recommend that companies who want to use graphene enhanced resins or in these systems, that they don't actually handle the graphene material itself, but they work with a compounder or someone who has experience in actually dispersing the material. And there were a couple of questions about folks asking, well, where can I buy this stuff? Where can I acquire some of this graphene enhanced resin systems? And I would invite you to contact the Graphene Council, because we do connect. That's what we're here for, is to help you connect with suppliers. And there are resin system suppliers, or another company that we've worked with, and one of our member companies, Composites One, which I'm sure everybody knows, is very much looking at this, at how to get this material into the supply chain. So I hope we answer some questions there. And Dan, I think you had another question.
And this question comes up from time to time, that this sort of graphene is in this nanomaterial universe, carbon nanotubes, maybe boron nitride and other materials. Can you talk about the distinguishing characteristics that make graphene different from some of these other nano-dimensional fillers or additives that could be used in composites?
One thing, the first thing being the surface area that is there when it comes to graphene. So typically, for example, the graphene in itself, when you look at the surface area, or the actual carbon itself, you have all the carbon atoms that are there for it to be used. So because of the surface area availability, you can actually use it for anything that you want. So you only need a limited amount of graphene for getting the right type of mechanical improvements and stuff. And another interesting is that when it comes to the viscosity increases, for example, in the resin, you don't necessarily see any sort of increase in the viscosity when it comes to carbon nanotubes, for example. Carbon nanotube bundles do normally increase the viscosity, which means you'd have to modify your processing techniques. Whereas when it comes to graphene, not many people have actually seen improvement in the viscosity, increase in the viscosity. So in the sense, you can use the existing procedure that you're actually using for producing the parts to necessarily do any sort of processing difference. And especially graphene is multifunctional, as I mentioned, so you can actually obtain the functional benefits of fire retardancy, and at the same time the mechanical properties, and also the hydrophobicity, for example, at the same time. So all three at one within just little amount of graphene, which may not be feasible for other type of dense materials, boron nitride or, for example, carbon black, for example.
I think there's an important point to highlight here, Dan, as well for the composites manufacturers. It was in the presentation, but just to highlight it. Using graphene in these resin systems does not require additional capital equipment. It does not require special processes other than the dispersion part of it. And I thought what was quite interesting is when you talked about the tools, because often we think about the parts, but we don't talk about the tools and the thermal properties and matching the thermal properties with expansion and contraction, et cetera, and the workability and processability. Maybe just talk a little bit more about that, because for manufacturers of those in the business end of this, that they need special equipment. Do they need special processes? Does it change how the material works in a negative sense? Can you just speak to that briefly? Because and I'll take this opportunity as well, because not everybody knows exactly what the GEEC is, the Graphene Engineering and Innovation Center at the University of Manchester. This is a dedicated facility that is designed specifically for rapid prototyping and using graphene materials in enhanced applications, composites being one of them, but also energy storage, coatings, films, etc. So it's specifically made to do this testing of prototype materials in an industrial type setting. So with that said, Mark, do you want to speak to that topic?
So around the tooling, and
processability and
I mean, from our experience that we've had in the Geek from using graphene enhanced prepregs, so handling prepregs, we've not seen any difference whatsoever. We haven't had to alter any cure cycles from regular prepregs or anything. So if someone's got, say, a resin system and they just add graphene to it, we generally stick to the same cure cycles and post cures, everything. So we don't actually have to change much at all. Depends how much graphene there is, and there is sometimes we had one experience where the prepreg was a lot tackier compared to what it normally would be, but we actually thought that was something to do with the original resin system, the batch that was done. So when we went back to the supplier, there was something wrong with that actual batch. It wasn't anything to do with graphene. So as far as we can see, there isn't a lot. There's nothing there really that prevents you from using it as normal. You can use all the same equipment, same processing, so cutting by hand or NC cutting machines, cure cycles, or whether it's in the press, whether it's in the autoclave, nothing's changed. So for me, the handleability is exactly the same as what it is before.
Thank you.
So you store it the same way as well, obviously, in the freezer. So it's still same resin systems. So still store it and just treat it as you would do a normal prepreg.
Excellent. Thank you.
Yeah, a question came up around the PAN precursor and the impact of final properties on the actual carbon fiber filaments. Do you have some data on that or some information to share?
Well, that's why I think I'll answer the question before in terms of that particular study was a very recent study in terms of the PAN adding graphene to the polyacrylonitrile, and it's very recent study in understanding just on a single fiber basis. So it's still in its early stages. There's not much of a data apart from that particular paper on at the moment.
Okay, thank you.
It's kind of scary to think. You mentioned almost a 200% improvement in the strength for the PAN fiber. Can you imagine using that and then enhancing the resin system with graphene on top of it? I mean, we're talking about an extraordinarily strong material. There's a question that talks about single-wall carbon nanotubes, multi-wall carbon nanotubes, and we, of course, have seen applications where graphene is used in combination with carbon nanotubes, often for electrical conductivity. But the question is about the trade-offs between cost and strength. Are carbon nanotubes, single-wall or multi-wall, actually quote unquote stronger than graphene, or how would you characterize using nanotubes either with graphene or instead of graphene?
I mean, in some cases, I see a synergetic effect between multi-wall the nanotubes and the graphene itself. So recently there are studies actually showing by adding graphene to carbon nanotubes or either way as a hybrid material shows a better improvement than a single on its own. But there is a little bit of improvement costs on also because carbon nanotubes being there for a little longer, so it's slightly lower cost when compared to the graphene, but graphene is definitely catching up into the price. Biggest match you can make, it's a synergetic match that you can actually make, and I mean if there is a small leeway that can be applied in terms of the viscosity increase by adding the nanotubes. I think that the improvements that you can actually get by adding both of the materials will be huge.
The comment I want to make is that often there is concern about graphene, which can be a high-priced material. The prices do vary widely on the grade and type and volume of the material. But when you're talking about a load factor of 0.1% by weight, even a nominally quote-unquote expensive material is not adding a tremendous amount of cost in the end application because such a small amount of it is being used. And the only advice that we would like to give in this area is the morphology of the material. And we haven't really covered the full range of the types of graphenes with a single carbon layer versus 2 layers versus 3 versus 5 versus 10, whether it's graphene oxide or reduced graphene oxide, whether it's functionalized or not functionalized. So there's many different iterations of what we call graphene materials. But, and I would ask both Mark and Arun to comment on this, how critical it is to tune or match the exact format of the graphene, the type of graphene, to your end application for the mechanical characteristics or other characteristics you're trying to get. And that's more important than I would say of just looking for a quote-unquote expensive versus cheap material. Does that make sense?
Yeah, definitely. I agree completely, especially the types of graphene-based materials, if you like, or ranging from graphene to graphene nanoplatelets. So graphene nanoplates is typically comparatively on a lower cost when the other type of material, graphene oxide or reduced graphene oxide. So based on the application you're developing, you'd want to choose the right type of application, right type of graphene. So if you're looking to improve the mechanical properties or the electrical conductivity of the material, then you would go for a high grade graphene nanoplatelets, for example. You wouldn't choose a graphene oxide, which is completely having a lot of oxygen groups. That isn't actually an insulator, so you wouldn't be using a graphene oxide material. So you have to choose. That's why I stressed at the beginning. So that is one of the commercial challenges in actually understanding the types of graphene-based materials that are there. So choosing the right type of graphene is crucial, and that's where you have to begin understanding different types.
That is one of the things that we do at the Geek as well. Is when someone comes to us with a project, is picking the right type of graphene for that application as well.
Excellent. So Dan, do you want to ask a closing question as we kind of go over the hour here?
Yeah, we're getting toward the end here, and thank you for all the folks who are sending in the questions. But you mentioned earlier on about the variability batch to batch and the need for standards for the graphenes. You just kind of touched on that. Just want to elaborate on that a little bit, to where you see the industry going in terms of classification of materials, developing standards, developing systems that people can understand and utilize in real world practices.
Definitely. So especially it was the case several years ago by a term, a graphene being used quite a lot, and it could have meant anything. It could have meant a black powder that you can buy. It could be called as graphene, but when you actually characterize it, it could be graphite basically. And that's where the standards for nomenclature came in a couple of years ago, that actually have cleared up what you should call this sub layer 5 should be called as fuel graphene. And so the vocabulary for the graphene based materials has been standardized now, and currently they are standardizing in terms of which characterization techniques that you probably have to use for identifying that particular piece of property. So, for example, BET for surface area measurements. So, I mean, these regulatory documentations are quite very important when it comes to the graphene-based material, or for anyone to follow. And that is currently being implemented, which is hugely beneficial for the end customers themselves, and also for regulatory bodies, and also for ourselves. Choosing the right type of graphene is whatever being sold as a black powder. Is it that what it says on the tin? So that is definitely very important. So it is going in the right direction.
People can find that information on the NPL, so National Physical Laboratory, the company who have been developing this nomenclature, so they can find that on their website as well. That is available.
Absolutely. I'll just restate it again. We actually had Andy Pollard from the NPL, who's he's one of the. We had a whole webinar dedicated on characterizing different types of graphene materials. So we have excellent resources available to help educate you. For those of you who are experts in composites, but perhaps not in graphene, we're here to help you understand this material. For those of you who are experts in graphene and want to look at opportunities into composites and into that industry, that's what ACMA is here for. And they have an excellent resource and network in composites. And so, that's what we're here for, is to help move this from the theoretical and the research phase into commercial applications, so we all can take advantage of materials that are better, lighter, stronger, more energy efficient, more robust and enduring. And with that, from my side, I want to say thank you. If Mark or Arun, if you have any closing comments you want to make, and Dan as well, I'd be happy to hear that. But from me, I'm very happy to have such knowledgeable experts on this topic, and to bring this to the audience that we have.
No, it's great. Thank you very much for the opportunity, Terence and Dan. That's great. Thank you very much, and good to see so many people attend. That's great.
Thank you. Same here. It's good to see a lot of interest. Several years before, graphene was just a hype, and now we're actually looking at graphene-based applications in a real-life scenario. That is very promising, and we're all here to just support anyone who actually looking to develop this application. So, thank you.
Yeah, I'd like to say just thank you both from the University of Manchester for bringing a lot of good information to our members in composite who are looking to apply graphene in so many different areas to explore. Seems like, Terence, we really have just scratched the surface here in regards to graphene and composites. So this was a great introductory webinar for our members. and maybe invite you all to a follow-up sometime in the spring, late winter next year, where we can dive into some of the topics that we didn't have time to explore in full today. But thank you very much. This was very enlightening.
Absolutely. Well, we appreciate the partnership that we've developed with ACMA over the years, and I think it just makes sense for us to continue working together to help our industry unleash this potential, because it looks really promising. Thank you, everybody. Stay safe and stay in touch. Thank you.
Goodbye.
Thank you.
Thank you. Bye-bye.
Thank you. Bye.